In the previous class, we started our discussion of the structure of detached shocks, and we looked at two situations, both involving flow over a wedge. In the first case, the semi-vertex angle of the wedge theta was less than theta max, corresponding to the free stream Mach number. So, supersonic flow approaches the wedge, and in this case we said that the the semi-vertex angle theta is less than theta max, corresponding to this Mach number. And in this case we saw that there is going to be an oblique shock which is attached to the vertex of the wedge, and the flow is then deflected through this. So, this is the direction of the shock wave, and the flow then passes through and goes like this. In the second case, we said that the vertex angle, semi-vertex angle, is more than or greater than theta max, corresponding to this Mach number. So, we had a situation where we were looking at something like this. So, the semi-vertex angle theta is now greater than theta max, corresponding to the free stream Mach number. And in this case, we had said that there was going to be a detached shock like this, and we had also qualitatively inferred that the strength of the shock is a maximum here, and becomes weaker because far away the free stream does not even know the presence of the wedge. So, that means that far away the free stream just goes through without any problem. So, this should be very strong here, and the strength should decrease as we go outwards. Eventually the strength will become vanishingly small, or this will become like an acoustic wave. That was one inference that we drew. The other thing that we said was, far away from the wedge the flow deflection angle was 0. The flow does not even know that the wedge is there, and at this point also the flow deflection angle is 0, but the flow deflection angle is non-zero in this location. So, we inferred from this that the flow deflection angle starts at 0, increases, probably reaches a maximum, and then again decreases to become 0 as we move outwards. Right. So, based on this we can correlate this with, for example, the theta beta m curve corresponding to this Mach number. So, let us say that this was our beta in degrees and this was our theta again in degrees. Now, if I draw the theta beta m curve corresponding to the free stream Mach number, that curve should look something like this, right. So, this is theta equal to 0, and this is beta equal to 0, and this is beta equal to 90. So, this is the theta beta m curve corresponding to this Mach number. Remember, the important point here is this is the theta beta m corresponding to this Mach number and represents the locus of all possible solutions for a attached shock wave, but here the shock wave is detached. So, whatever we are going to say is going to be only qualitative, not quantitative, but by and large the qualitative inferences seem to be accurate when you look at solutions obtained using a very complex CFD calculation, for example. So, the inferences are qualitatively consistent and accurate, which is why we are going through this exercise. So, if you look at this curve, if I start from here, the flow deflection angle here is 0, and then as I go along this, the flow deflection angle increases, reaches a maximum. Then when I come down, the flow deflection angle decreases and becomes a 0 here, and that was exactly what we said was happening along this curve. What we said should happen along this curve, that the flow deflection was 0 here and 0 there, so reaches a maximum somewhere in between. Let us see whether this is consistent with the other inference which we said about the strength of the shock wave or loss of stagnation pressure. And again you notice that the loss of stagnation pressure or the strength is very high at this point. Then as I move along this is the strong shock branch, it becomes weaker and continues to become weaker once I move into the weak shock solution, and then becomes the weakest, infinitesimally weak when I reach the Mach wave solution or the isentropic wave solution. So, this is the strong shock branch, and this is the weak shock branch. So with regard to the strength of the shock wave decreases continuously from strongest here to weakest here. Flow deflection angle is also consistent with what we had inferred. So we can say that from here, this point of the shock wave represents a normal shock solution, and as I move here, there is going to be some part which is part of the strong shock, and there is going to be some part which is going to be the weak shock solution. This is a qualitative inference. This is how we expect this to be. So you can see that we are actually able to see a strong shock now. Previously we said that attached strong shocks are seldom seen, probably never seen, but detached strong shocks can be seen and are seen in many real life applications. As I said, when a missile or a space vehicle re-enters the atmosphere, the bore shock ahead of this will have a strong shock portion and a weak shock portion. But this has other implications. If you remember, we said that for the strong shock solution, M2 is always less than 1, and for the weak shock solution we said that M2 is almost always greater than 1, almost always, except for a small portion here. M2 here is almost always greater than 1, correct? So what that means is that the flow, when it comes across this part, the M is going to be less than 1 here, and the flow when it comes across the weak shock portion, the M is greater than 1, which means that there is a sonic line in between these two. So I can draw a similar thing on this side also. So we will have a strong shock here and weak shock here. So M is less than 1 here and M is greater than 1 here, which means that we are going to have something like M equal to 1 sonic line. So this represents M equal to 1. Okay. So the pressure increases across this, static pressure always increases, but then the flow is actually accelerating when it goes across the surface of the wedge in this case. So the subsonic flow accelerates and attains the supersonic velocity. Eventually it attains the free stream speed if you extend this law, if you terminate this in some fashion. We really cannot go into that part because we need to know how this is terminated. Okay, so that is a much more complicated thing, but you can see for now that the flow deflection has to be very large here, and the flow deflection then gradually eases out and then it becomes parallel to the surface of the wedge. So same thing here, same thing here. Yeah, but what is interesting is that the flow actually accelerates when it goes across like this, across the surface of the cone. That is something that you probably would not have expected to begin with. So, but these inferences, these are only qualitative inferences, and these are actually reasonably accurate when you do a 2D simulation of this particular flow. And because this is of use in many, this occurs in many applications, you can get very good ideas about pressure rise across the wave and other flow features just based on this. Okay. The important point is you see this kind of strong shock solution only in these types of situations, not attached strong shock solutions. Any questions? So the next topic that we are going to look at is the reflected shocks. What happens when an oblique shock wave impinges upon a surface? So far we were talking about a corner like this at, let's say, at certain angle theta. So we said supersonic flow, let's say M1 greater than 1 approaches this type of a corner, and we had an oblique shock wave that was generated at the corner, and then the flow went like this. So let us call this 2 and let us call this 1 before this, and we looked at the flow and how the shock wave is deflected and so on, and this angle was denoted as this angle in our usual notation is denoted as beta 1. Okay. What happens when this kind of a oblique shock is triggered inside a duct? In other words, let us say I have a wall like this. So we have a duct in which we have this corner, and what happens when this shock goes all the way? So remember, there is also a direction to this shock wave, and let us indicate that explicitly. So this is the direction. The question is, some of the questions are easy to ask, but the answers are not obvious. The question is, how does this shock wave come back? Does it come back? If it comes back, how does it come back? Is it like a reflection from a mirror, or the angle is the same or not? Those are the things that we need to discuss. Let us see what happens. Let us say that I do not know how the shock comes back. I do not know whether it comes back as a shock, whether it comes back as some other wave. Remember, there are many wave solutions that are possible. Let us say that it comes back as something, but I know for sure that the direction is going to be this, on this wave. Let us say this is an unknown wave, but the direction is known, correct? And I also know that the flow, after it passes through this, what is the direction of the flow? The flow has to be parallel to the top wall, we know that for sure, right? So the flow direction has to be this. So the flow goes into the wave like this and then comes out like this. So that means it is deflected towards the wave. So that tells me that this is going to be a oblique shock wave. So now I can remove this and say that this is going to be reflected as a shock wave. So that answers my first question. It is reflected, and it is reflected as a shock wave. You may wonder why this is so obvious. It has to come back as a shock wave. In the next chapter, when we look at reflection from a constant pressure boundary, like a jet boundary, you will notice that it does not come back as a shock wave, it comes back as something else. So how it comes back is determined by the fluid dynamics of the problem that we are looking at. So in this case, because the flow has to be straightened out parallel to the wall, it has to reflect as a compression wave, because we need to deflect the flow towards the wave. Okay. So now the question is, what about the angle? So we know that this angle is beta 1, correct? What about this angle? What is this angle equal to? Is this equal to beta 1 or is it something else? That is the next question that we must answer. And remember, in oblique shock wave, the angles are always measured with respect to the velocity vector ahead of the shock wave. So if I look at this, this is the velocity vector ahead of this shock wave. So that means this angle is theta 1, or this angle is theta. And what is the wave angle now? The wave angle is theta plus this angle. So this is the new wave angle, beta 2. Right, and m2 is less than m1. So if I go to my theta beta m diagram, let us say that this is the curve corresponding to m1. And the curve corresponding to m2 is less than m1, so the curve corresponding to m2 is going to look like this. What is the flow deflection angle for the second shock wave? Same as the previous one. So if I draw a horizontal line, let us say this is my flow deflection angle theta in this particular problem. The previous situation had this as my beta 1, correct? In fact, this is a little bit confusing, so let me write it like this. So let me call this beta 1, right? So I want the same deflection angle, but now the Mach number has reduced, which means that my deflection angle is now going to be higher. So I am going to pick up this solution for the same angle, this will be my beta 2, which tells me that this reflection is not necessarily going to be at the same angle. That angle is determined by m2 and the fact that theta is a constant. Okay. So if everything is okay, then the shock is reflected back this way. I can actually calculate beta 2 from my theta beta m table, there are no issues. So this is what is called a regular reflection. So we have an oblique shock, it is reflected back as a regular oblique shock wave with a different wave angle. But there can also be some difficulties with this reflection. There is also another type of reflection. Notice that the way the theta beta m curves are, right, the way the theta beta m curves are, because we are operating at, let us say this is the deflection angle and this was my initial wave angle, now this is my new wave angle, right, m2 decreases, so everything was okay. What happens if my initial flow deflection angle is like this? This is my, if this is my initial flow deflection angle theta, right. So I increase this angle, it is still less than theta max for this Mach number, okay. So this would be my initial beta 1, but the Mach number decreases, right, m2 is less than m1. So you see that a regular reflection is not possible in this case, because there is no solution, we do not get a beta 2. So a regular reflection is not possible in this case. So what happens in this case is that we get a flow which looks like this. So the first oblique shock can be generated without any difficulty, right. This is theta and this is beta 1. So the first shock wave can be generated without any difficulty, and the arrow on this looks like this and the flow is like this. But then that curve tells me that a reflection, regular reflection is not possible. So what happens in these cases is that you generate a normal shock here close to the wall, and then the oblique shock comes back like this, okay. So this is a normal shock. This type of reflection is known as a Mach reflection. So an attached oblique shock solution is not possible in these cases. So we have a normal shock wave, then the flow comes back like this. But when you have these types of situation, notice that if you take a streamline which goes through, there is no flow turning here, right, there is no flow turning across the normal shock wave. So if you look at the flow which goes through like that and another one which goes through like this, right. So this is the streamline which goes through like this, deflected this way and then deflected back again this way. So this is the other streamline. If you look at the entropy change across this one, the entropy change is going to be higher because it goes through a normal shock. But if you look at this one, the entropy change is going to be less because it has gone through two oblique shocks, which means that in these types of situations you get a new structure called a slip line. A slip line is a discontinuity in the flow field. Normally velocity is discontinuous, entropy is discontinuous, but pressure is continuous across a slip line. So across a slip line, velocity entropy or discontinuous normally pressure, static pressure is continuous and temperature too. Yeah.
How come static temperature can be same? Because normal shock will have higher
Yeah, no, static temperature normally in real flow you are going to have other mechanisms which will cause the temperature to equilibrate, but from a gas dynamic solution static temperature will also be discontinuous. Yeah, that is correct.
What is the extent of the normal shock? Will it
That-
be determined by the theta max?
That is, yes, that is determined by where you are operating in this curve. Okay, where how far away you are from this theta max. The farther away you are, the greater the extent of the normal shock will be. Okay, because if you operate, if this theta is such that let's say you are just over here, then still attached shock solutions are possible. Let's say you increase it slightly, yes, just barely. So that means now you are beginning to get the normal shock portion. So the farther away you are from the theta max corresponding to M2, the greater the normal shock portion. Yeah, go ahead.
How does the reflection depend on the surfaces? So surface should anyway turn to be horizontal at some point of time, but then there will be discontinuity again.
There will be, yes, normally what is done is, yes, that's a good question. Normally what is done is, if you want further reflections, then you do something. If you want to terminate the shock, how do we terminate the shock? You can terminate the reflections. If you don't like them, you can do the following. You adjust this angle in such a way that after this the flow is completely straightened out and the shock is terminated. It is possible to do that. Okay. So in some cases you may want several reflected shocks to achieve further compression before you go to the next component. So depending upon what you want, you can either terminate the oblique shock at some point, or you can also have multiple reflections. So if you want to terminate, then this theta can have only a certain value. So you can determine that from this combination and then do that. One of the exercise problem asks you to do that.
So does the reflected shock exactly come at the point where we turn it? Or?
Yes, yes. So the reflected shock comes and impinges at this corner. Remember, if you look at this corner, we are going to see this in the next chapter. What type of a corner is this? Generally, if you look at the flow, let me draw this separately so that it is not confusing. We have to look at the corner in isolation. Excuse me. You have to look at the corner in isolation. So if you look at this, so I had a flow which came like this, I have a flow which comes like this, still supersonic, right? So M is still greater than 1, M1 is greater than 1. So the flow has to go around this corner now, which means that I am going to generate some wave. I don't know what that wave is. I need not assume anything about the wave. I am going to generate some wave from this corner, at some angle, let us say some wave like this, but I know for sure that the direction of the wave, let me change the color, I don't want it to have the same color as the other one, let us use yellow. So I am generating some wave here of an unknown type, but with the direction like this. So after passing through the wave, the flow has to be like this. That is our intent. We don't want any reflection and we want it to be parallel to the surface, right? So how are we turning the flow in this situation? We are turning the flow away from the wave. So whatever the wave is, it has to be an expansion wave. So now that is what happens if you look at this corner in isolation. Now you look at the corner in combination with this one. So you are generating an expansion fan here, and an oblique shock is also incident upon this corner. So the two cancel each other and we get a flow free of reflections. Okay? Yeah, that kind of design has to be done very carefully. It is always done in intakes. In fact, we will go back and revisit one of our worked examples. You will see that definitely happens in practical intakes. And this will have a lot of implications later on. Such reflections will have a lot of implications later on when we look at, for example, fan blade. We are going to look at propulsion, right? That's our objective. So when we look at fan blades, you will notice that we are operating with a transonic fan blade. which means part of the fan blade has to compress, decelerate and compress a supersonic flow in the blade passage. So that means the passage has to be designed properly, and it is very difficult to avoid such expansion corners. The Mach number increases across the expansion corners, which means I have to bring it down again, which means loss of stagnation pressure. So the design is very tricky for in these types of situations, but a knowledge of gas dynamics is very, very important. So people have designed very clever blade profiles for fans where you have controlled diffusion so that you avoid these types of problems. Such sections are called controlled diffusion airfoil, CDA, and we will look at that when we talk about fan blades. Because gas dynamics, we started the lecture by saying compressibility effects are significant in inlet, fan, compressor, turbine and nozzle. That is why we are going through in such detail. Every one of this concept that you learn here will be very useful later on when we look at propulsion. Okay. So technically that completes the discussion of this chapter. What I wish to do now is to continue the worked example that we looked at in the previous class. I was kind of unhappy with the way we left it, so I am going to revisit this worked example. And we said that normally there will be a terminal normal shock here before we complete this compression process. Let us go ahead and do that, continue the worked example with a normal shock here, and then look at the stagnation pressure recovery in the intake as a result of this. Okay? So that will just take a few minutes. Let us go ahead and do that. One of the most important things that you should learn from this chapter is the theta beta m curve. You should be able to draw the curve completely and know every aspect of the curve. That is an extremely important curve in real applications, because the possibility of solutions, detached shocks, attached shocks, other things, strength variation and so on, all of them are tied to that single curve. So you should know the behavior of the curve, should be able to reproduce the curve at any time. So let us continue our worked example. So what we are doing is the following. So this was the intake that we looked at in the previous class. Now I have added a normal shock at the end of the compression process so that the flow becomes subsonic as it goes inside the intake, and we want to look at P03 over P0 infinity to see how effective the shock wave compression process is. Okay. Once again, notice that in this case also there is an expansion corner here. So the flow will actually try to accelerate around this expansion corner, and that is something that you have to deal with, because we are trying to decelerate the flow, but there is going to be local acceleration around this. So we try to design things in such a way that this is minimized. Okay, and we are still operating with the quasi one dimensional or slightly better than quasi one dimensional assumption. So this is the best that this theory can provide. Okay, so let us go ahead and have a terminal normal shock and calculate P03. So we used to calculate P03 over P0 infinity. And let me just quickly recap whatever we had calculated in our previous class. So if you remember, we had calculated our M2 so was 1.712 if you remember, and P2 was 95.282 kilopascal, and T2 was 240 Kelvin. This is static temperature. So now we are going to have a normal shock at 1.712. So we go to the normal shock table. From the normal shock table, for M2 equal to 1.712. So this will go into the normal shock table as M1, right? So we go to the normal shock table with this value of Mach number and we retrieve the following quantities. We have P3 over P2 static pressure ratio 3.2449, T3 over T2 1.465535 and M3 is equal to 0.638. And in this case, because it is the normal shock wave, I can also retrieve P03 over P02 0.8515385. So you can see that the Mach number finally becomes subsonic after the normal shock wave. So P03 over P0 infinity can be written as P03 over P02 times P02 over P2 times P2 over P1 times P1 over P infinity times P infinity over P0 infinity, right. We have calculated all these values during our earlier calculation. So let me just substitute the numbers 0.8515385 times 5.049225 times 2.25253 times 2.82 divided by P0 infinity over P infinity will go into the denominator as 36.7327. Okay, so this quantity is P0 infinity over P infinity. So if you calculate this, this comes out to be 0.74 or 74%. And remember, M infinity was equal to 3. So M infinity is equal to 3 in this case. So from M infinity of 3, we have decelerated the flow to a Mach number of 0.638, and in the process we have lost about 26% of stagnation pressure. This is called the stagnation pressure recovery, 74%. We have lost 26%. The same compression, if we had done using a single normal shock, we can check that also. If you do the same compression using a single normal shock at Mach 3, for a single normal shock compression, we get the final Mach number M3 to be 0.475 and P03 over P0 infinity comes out to be 0.3283 approximately 0.3283. So you can see the tremendous difference that the oblique shock compression makes. So here we are losing only 26% of the stagnation pressure, here we are losing nearly 68% of the stagnation pressure. So you can see how much more better this is if we can do it in a stable manner. These intakes are not without their problems, okay, and that is something that we will discuss when we in the later part of the course when we talk about supersonic intakes. But this demonstrates very clearly how much better the oblique shock wave compression process is. And for this reason alone, I wanted to continue the example and finish it off today. So now we go to the next chapter. This is the last chapter that we will discuss in gas dynamics, Prandtl Meyer flow. So here we are going to talk about oblique expansion as well as compression waves, but waves which are isentropic. So we are going to look at isentropic compression / expansion waves. And to see how how these waves are generated, we start our discussion by looking at the following figure. So here we are looking at point disturbance. Okay, so this is a very small object, almost like a point. So a point disturbance is traveling from right to left with a speed equal to u. And I have sketched the location of this object at different instants of time as it passes through like this. So for every delta t increment in time, the object goes from here to here. So I have shown the object in increments of delta t. The object is traveling continuously, but I have shown this only in increments of delta t like this. So when this point disturbance starts moving, when it starts, the moment it starts moving, it starts generating these acoustic disturbances which travel outward, as you can see, with speed equal to speed of sound. So these are spherical wavefronts in 3D, and these move out with speed equal to the speed of sound. And I have also shown these wavefronts at different instants of time. So for example, if you are here, then the wavefront that this generated would have traveled a delta t in a time delta t, and the wavefront that was generated by this would have traveled 2a delta t in the same time, and so on. So you see these waves expanding outwards, but a new wave being generated at every instant as the disturbance passes through undisturbed fluid. Right. So this is how it happens. So any observer who is located somewhere, the observer can be located anywhere in this space. So any observer who is located here will actually hear the disturbance before he sees the disturbance in some case. So you get to know of the disturbance even before the source arrives to the person. Okay. For example, a person standing here would have heard the disturbance long before the source actually arrives at his location, because the source is moving with the speed which is less than the speed of sound. So you can see that the source is moving with the speed which is less than the speed of sound. So the disturbances are seen by the observer before the source of the disturbance actually arrives. If I increase the speed of the source to a speed equal to the speed of sound, then you can see what happens. Right. So the source, as you can see, the point disturbance is always just at the wavefront of the wave that it generated delta t or any of the previous instances. So the source is always at the front here and moving along with the wavefronts as it is generating new waves, but it is also keeping up with the waves. So in this sense, an observer who is standing, let's say, somewhere here gets to know about the disturbance and the source of the disturbance at the same time. Both arrive at the same time. Both the disturbance and the source that makes the disturbance arrive at the same time. That is when the speed with which the disturbance moves through the still air is equal to the speed of sound, local speed of sound. One very important point that you should always keep in mind here is that this type of scenario is possible only when the source of disturbance is a point disturbance. It is not an object of finite dimensions. It is an infinitesimally small point. For example, if a bullet moves through the air, we will not get the same situation because it is a finite sized object. If it is a finite sized object, then we are talking about oblique shock waves. This is an infinitesimal point object, so we get this scenario only in this case. So this is a very special case. Now what if I increase the speed of the disturbance even more? Right? Let us say that I make it travel with supersonic speed, right? Then this is the situation I have. Let me rotate this view so that we can see this better. So that we can see this better. Now you can see that the disturbance is beginning to travel in such a way that the observer, any observer who is located along the axis of this, sees the source of disturbance passing by before information about the disturbance itself arrives there. Okay. So, the observer, as you can see from here, an observer who is located here will see the disturbance passing by, but any information about the disturbance that it has created will be received only after the source has passed by, which means that the region in which the disturbance is going to be felt as a result of passage of this is confined to this cone shaped region. So, you see a cone here. So, all the information about the disturbance is contained here. Anyone outside this cone will not hear anything, will not know that something has passed. The observer will come to know about the disturbance only after the observer gets into the zone, into the cone. In other words, the cone is going like this. So, when the cone passes over the observer, that is when he actually knows about the disturbance, but the disturbance itself has long gone, right. So, that is why this is called the zone of action. Any information about the disturbance is confined to this cone shaped surface in 3D flow. Nothing is known about, nobody here will know anything about the source. This region is a region, so the source itself is affected, or the source itself can see only disturbances which are confined to this zone of dependence. If the disturbances are confined to this zone of dependence, then the source can perceive or see only these disturbances. If there is a disturbance that takes place here, the source will be oblivious to these kinds of disturbances. In other words, if I want to influence the source in some way, I need to make sure that I do it within this region and not outside this region. So, I get distinct regions where information is available, where information is not available, and regions which allow me control, and other regions in which I do not have any control. So, that happens when the source begins to travel with the speed which is greater than the speed of sound. Okay. So, the source is always ahead of the waves that it produces. Now, in such a situation, as you can see from here, the surface of the cone is like a wave front. In addition to these wave fronts, right, each one of the surface of this spherical wave front is also a wave front. In addition to these wave fronts, we also have the surface of the cone itself acting as a wave front, as you can see from here, and that is given the name Mach wave. So, there is a discontinuous change in flow properties across the surface of the cone. So, that itself actually behaves as if it is a wave. But because we are talking about sound waves and acoustic disturbances, the changes across such waves are infinitesimally small and the processes are isentropic, which is why we said that we are going to look at isentropic compression and expansion waves. So, the process across this Mach wave, notice that the process across the Mach wave can be a compression or an expansion process. In this particular case, we talked about the source starting from subsonic speed and then accelerating to supersonic speeds. What about a source which decelerates from a supersonic speed to subsonic speed? So, the flow will be exactly the opposite. In one case you get expansion, in another case you get compression, both being isentropic. So, we are going to look at isentropic compression expansion solutions. The solutions are called Prandtl Meyer solutions. The wave itself is called a Mach wave. So, we will pick this up in the next class and then discuss this in great detail.